Cool. All right, so we've talked about QC. Remember, QC is at any point in the reaction, and KC is at the point at which the reaction is at equilibrium, right? So let's link QC and KC. QC is at any point in the reaction. QC equals KC if the reaction's at equilibrium, right? So what happens when, if we look at, so remember we looked at our graph of, say, the Haber process reaction we were looking at. We had, so we had nitrogen here, we had hydrogen up here, and we had the formation of ammonia, right? So over time, ammonia increases, right? Nitrogen decreases, as well as hydrogen decreases, okay? So initially, QC would be 0, right? Because there's no products. So let's look at, say, at a particular point in time, let's just call this, I don't know, some point, let's call that T1. So at T1, after a little bit of the reaction, the value of QC would be something like this, and the value of the equilibrium constant will be something like this. Wrong symbols, KC, right? So when QC is less than KC, right? When QC is less than KC, what's the effect of that reaction? So we're going to have a net forward reaction, aren't we? Because we're wanting to form more products in order for QC to come up to the value of KC, right? In order for the reaction to then return to equilibrium. Yeah. So if QC is less than KC, we have what's called a net forward reaction. Why do I use the word net forward reaction rather than a forward reaction? Right. As soon as we start to form products, we start to have the backwards reaction occurring. It's just occurring at a lower rate than the rate of loss of product. So that's why it's a net forward reaction. And so we would say in this reaction, net forward, or we'd say the reaction shifts to the right is one way to consider it either. I try to avoid using right and left. Same thing as why I don't use right and left when talking about galvanic cells. So use in terms of either a forward or backwards reaction. Let's have another scenario in which I had a vessel in which I started with ammonia. So if I started with ammonia for that same reaction, so this is, say, starting with N2 plus 3H2 goes to give 2 NH3, starting with no NH3, starting with some N2 and H2, the reaction shifts forward. If I only start with NH3 but still represent the reaction as the same, and if I start with NH3, what's going to happen? I'm going to lose NH3, and I'm going to gain some N2, and I'm going to gain some H2. And so we see in this reaction, I've only got products. So in this example, the value of my QC would be much higher than my equilibrium constant. So therefore, if the equilibrium constant is greater than Kc, we have a net backwards reaction. Or it shifts towards the left. Right, if I just make that more obvious, the difference. Shift toward left. Right, and when QC equals Kc, no change, no shift. Change in the direction of the reaction. Yeah, there's no shift. To still have the forward and backwards reaction occurring because the reaction is at equilibrium. So looking at that this table, if I have 0.0011 molar of nitrogen, 0.0011 molar of hydrogen, and 2.7 by 10 to the minus 7 molar of ammonia, that reaction is already at equilibrium and we won't have that shift, right? So if I put it in the appropriate quantities, we're not going to have any change in direction of reaction. Cool. Let's now consider, what I want to consider is, let's look at another example. I want you to write the expression for the equilibrium constant for the following reaction. I have H2 gas plus I2 gas goes to give 2HI gas, right? Ensure to include units. So, trick question with the units. There are none, because I've got molar squared divided by molar squared, which cancel out, right? So highlighting the fact that units change with equilibrium expression. Yeah, exactly right. So write the equilibrium expression for the following reaction. Should be easy. Right, so Kc equals to concentration of H2 times concentration of I2 on the concentration of Hi squared, right? So we can make a general statement about this. If I write the reverse reaction, the value of Kc will be the reciprocal i.e. 1 on Kc of the forward reaction. Yeah? Make sense? So what do we do to delta H when we reverse the reaction? We change the sign. Yeah? So what we do to the value of Kc is we take the reciprocal. Yeah? All right, let's do something else. Let's go back to that first equation. And I'm going to go write the expression for that reaction. We'll have noticed that if we write the equilibrium expression of this reaction, Hi to the power of 4, H2 to the power of 2, I2 to the power of 2. Now, if we know our indice laws, right, I could rewrite this as Hi all squared on H2 times I2 all squared. Make sense? Yeah? So the effect of doubling the coefficients right, squares the value of KC. Yeah? No. How would you simplify that? You can't divide it by 2. It's not a coefficient. It's to the power of. The only way to get rid of that is doing what? Well, yeah. But that's not what I'm trying to highlight. If you double the value of coefficients with delta H, if you double the value of the coefficients, what happens to delta H? Doubles delta H, right? Because you're doubling the amount of mole, so therefore you double the amount of energy. If I double the concentration of all the chemical species, I square the value of Kc. Yes, in terms of balancing a chemical equation, yes, we can simplify that down to whole number ratios, right? But in practical sense, I can double the concentration of all chemical species. Yeah? Can do that by halving a volume. That doubles the concentration of everything. Yeah? Cool. Similarly speaking, let's look at another example. Let's take, I don't know, what's a good example? If I take, all right, let's just take the original reaction again. What would the expression of that be? Yeah, exactly right. Yes, anything to the power of a half is the same as the square root. So the expression for this would be hi, h squared to the half, by 2 to the half, right? Which is the same as hi times the square root of h2 by I2, which is, right, the square root of hi squared on h2 I2. So therefore, halving the coefficients, halving the coefficients take the square root of the value of Kc. Yeah?